Good day, future engineers. We are Group 1 of BSME-SEP 2A from Technological University of the Philippines. Today, we are about to tackle actual Rankine cycle. But before that, let me introduce to you our members. Belar Jun Lim Philippine, Catalina John Rubel, Durban Angelu, Lazona Brian Jason, Mangondato Jig, Peñalosa Adrian Paul, Saltes RJ, Tarokin Leilani, you Sean Carlo, and yours truly, Michika Morales. But before we start, let us have a short introduction about Rankine cycle. What is Rankine cycle? The Rankine cycle is one of the popular cycles widely used by power plants. It is used to convert the pressure energy coming from the steam to mechanical energy with the help of steam turbines. Basically, the Rankine cycle is a kind of cycle that describes the process by which the heat engines or steam engines allow to be extracted from fluid such as steam in steam power plants. The heat sources from which the power plant uses the Rankine cycle are coal, natural gas, or oil. There are four major components of Rankine cycle, including a rotating steam turbine, a boiler pump, a stationary condenser, and a boiler. There are four processes of Rankine cycle. First, cycle point 1 to point 2, or the isentropic expansion in the steam turbine. The vapor is expanded in the turbine, thus producing work which may be converted to electricity, where S sub 1 is equals to S sub 2. Next is from point 2 to point 3, or the isobaric rejection of heat in the condenser. The vapor-liquid mixture leaving the turbine is condensed at low pressure, usually in a surface condenser using cooling water, or P sub 2 is equals to P sub 3. Next is from point 3 to point 4, or the isentropic compression in the feed water pump. The pressure of the condensate is raised in the feed pump, where S sub 3 is equals to S sub 4. Lastly, from point 4 to point 1 is the isobaric addition of heat in the boiler. High-pressure liquid enters the boiler from the feed pump and is heated to the saturation temperature, where P sub 4 is equals to P sub 1. Processes of actual Rankine cycle will be slightly different with the processes of an ideal Rankine cycle, because in practice, there will be various irreversibility in various components of Rankine cycle. Heat losses to surrounding and friction will be the main causes of irreversibility, and we will also discuss here the deviation of actual vapor cycle with the ideal Rankine cycle. So the compression and expansion by pump and turbine are not isentropic. Basically, these processes are non-reversible and the entropy is increased during the two processes. It does not remain constant. So it will increase the power required by the pump and reduce the power generated by the turbine, mostly due to water droplets formation. As the water droplets will condense, water droplets will hit the turbine at a very high speed and the turbine will get eroded. The blades and efficiency of the turbine will be reduced. The solution, like superheating of steam, are employed to overcome these problems. So to overcome the losses and get more net power output, some variations are adopted in the Rankine cycle. So here we have the ideal work. It is the work of the reversible adiabatic expansion process in the turbine. Next is the indicated work. Is the work of the irreversible expansion in the turbine. We also have the brake work. It is the available in the turbine shop, and the combined work is the electrical energy generated in the generator. Then, the ratio between the brake power all over the indicated work is called mechanical efficiency, while the ratio between combined power all over the brake work is called generator efficiency. There are also several parameters of actual simple Rankine cycle. We have engine efficiencies, steam rates, and the heat rates. Under engine efficiencies is the indicated thermal efficiency, where work indicated all over energy chargeable. Next is the brake thermal efficiency is equals to brake work all over energy chargeable. And the last one is combined thermal efficiency is equals to work generated all over energy chargeable. Under steam rates is the indicated steam rate is equals to 3,600 seconds per hour all over work indicated. Brake steam rate is also equal to 3,600 seconds per hour all over brake work, and the combined steam rate is all over work generated. Next is the heat rates. Under heat rates is indicated heat rate is equals to indicated steam rate times the energy chargeable. Next is brake heat rate. It is equal to brake steam rate times the energy chargeable. And last one is the combined heat rate is equals to combined steam rate times the energy chargeable. So here's the problem. A Rankine cycle operates between pressures of 2 megapascal and 10 kilopascal with a maximum temperature of 600 degrees Celsius. If the insulated turbine has efficiency of 80%, calculate pump work, heat added, heat rejected, energy chargeable, ideal turbine work, and then ideal network, engine thermal efficiency, cycle thermal efficiency. Next is actual turbine work, actual network, actual cycle thermal efficiency, and then actual engine thermal efficiency, actual entropy, turbine efficiency, actual temperature of the steam of the exhaust, and lastly is the actual condition of the steam at turbine.
At sa point 1, P1 equals to 2 megapascal, T1 equals to 600 degrees Celsius. Tignan natin siya, isa siyang superheated. So, hanapin natin siya sa table 3, which may kita natin yung ating enthalpy 1 equals to 3,690.1 kilojoules per kilogram. Ang ating entropy 1 equals to 7.7024 kJ per kJK. At point 2 naman, may ano natin na S2 equals to S1 equals to 7.7024 kJ over kilogram Kelvin. Then next is yung P2 or pressure 2 equals to pressure 1 is equals to 10 kilopascal at convert natin sa megapascal is maging 0.010 megapascal. At kung check natin mula sa table 2 na steam table is makukuha natin yung enthalpy saturated liquid which is 191.83 kilojoules per kilogram. Ang ating HFG equals to 2,392.8 kilojoules per kilogram. Para naman sa ating entropy saturated liquid equals to 0.6493 kJ over kJK, and for ating SFG equals to 7.5009 kJ kJK. Para makuha natin yung steam value equals to entropy 2 minus entropy saturated liquid over SFG, which is maging equals to 7.7024 minus 0.6493 divided by 7.5009 times 100%. Ang magiging steam value natin is 94.03%. For H2 equals to HF plus steam value times HFG equals to 191.83 plus 0.903 times 2,392.8. Kalabasan natin, makuha natin H2 equals to 2,441.78 kJ per kg.
So, we now proceed to our point 3 and point 4. At point 3, according to the principle of Rankine cycle, may isobaric heat rejection na nangyayari sa point 2 to point 3. Meaning, dito sa condenser, ang steam na lumabas ay nagiging saturated liquid. And then, according pa rin sa principle ng Rankine cycle at point 3, the pressure is constant since P3 is equal to P2. And by knowing that, we have a pressure of 0.010 megapascal. And upon checking the steam table, the enthalpy is 191.83 kilojoules per kilogram, while yung specific volume for our saturated liquid is 0.0010102 cubic meter per kilogram. And now we proceed to our point 3 at point 4 rather. At point 4, we want to know the value of our enthalpy, yung H4. We know that we have a formula for solving H4. So H4 is equal to H3 plus the approximate pump work. Since wala pang value yung for our pump work, we need to use the formula approximate pump work is equal to V3 to the quantity multiplied to the quantity of P1 minus P2. Then, by substituting the values, we have approximate work of 2.01 kilojoules per kilogram. Then, since meron na tayong value for our pump work and H3, we can solve the H4. Then, by substituting the values, we will have H4 with the value of 193.84 kilojoules per kilogram.
The first that is asked for the Rankine cycle is letter A, pump work or approximate pump work. The formula for pump work is WP is equal to B3 times the quantity P1 minus P2. Now, to get this, we need to get the specific volume, the given pressure at point 3 or V3. Looking at our steam table on page 8, look for 0.010 megapascal. Take note that the unique condition in point 2 to 3 is saturated liquid. Therefore, our specific volume is 0.0010102 m3 per kilogram. Substituting the given to the formula, WP is equal to 0.0010102 times the quantity 2000 minus 10 is equal to 2.01 kilojoules per kilogram. The next one is letter B, heat added. Heat added or QA. The formula for this is QA or heat added is equal to H1 minus H4. Since H4 is not given, we have to compute it using the formula H4 is equal to H3 plus the pump work. Substituting the given, H4 is equal to 191.83 plus 2.0103 is equal to 193.84 kilojoules per kilogram. Now, going back to heat added, we're just going to substitute all the given to the formula. QA is equal to H1 minus H4. So, QA or the heat added is equal to 3690.1 minus 193.84 is equal to 3496.26 kilojoules per kilogram as our heat added. Next one is letter C, heat rejected. The formula is QR or the heat rejected is equal to H2 minus H3. Seeing that H2 and H3 is already given, we're just going to substitute QR is equal to H2 minus H3 is equals to 2441.78 minus 191.83. That will give us 2249.95 kilojoules per kilogram.
For the energy chargeable, the givens are H1 is equals to 3690.1, H3 is equals to 191.83. The formula is energy chargeable is equals to H1 minus H3. By substituting the values, Solution is 3690.1 minus 191.83. So, our energy chargeable would be equal to 3498.27 kilojoule per kilogram. For the ideal turbine work, the givens are H1 is equals to 3690.1, H2 is equals to 2441.78. The formula is the turbine work is equals to H1 minus H2. By substituting the values, the solution is 3690.1 minus 2441.78. So, the ideal turbine work is equal to 1248.32 kilojoule per kilogram. For the ideal network, the givens are the turbine work is equals to 1248.32, the pump work is equals to 2.01, the formula is the network is equals to the turbine work minus the pump work. By substituting the values, the solution is 1248.32 minus 2.01. So, the ideal network is equals to 1246.31 kilojoule per kilogram.
G is the engine thermal efficiency. The formula for the engine thermal efficiency is ideal turbine work divided by energy chargeable, and the quotient of the two will be multiplied by 100. Since we already know the values for the ideal turbine work, which is 1248.32, and the value for the energy chargeable, which is 3498.27, we just need to plug in the values in the formula, wherein we will get the value for the engine thermal efficiency, which is 35.68%. Later, we will solve the cycle thermal efficiency. The cycle thermal efficiency has the formula of ideal network divided by the heat added, and the quotient of the two will be multiplied by 100. Since we already know that the ideal network has the value of 1246.31 and the heat added has the value of 3496.26, we just need to plug in and substitute the values in the formula, and we will get the value of the cycle thermal efficiency, which is 35.65%.
So the value of H2 is equals to 3690.1 kilojoules per kilogram, and the value of H2 is equals to 2441.78 kilojoules per kilogram. And the answer for the turbine work will be 1248.32 kilojoules per kilogram. Now that we have the value of the turbine work, we can now use it for the formula of the actual turbine work, which is WA is equals to WT times the given engine efficiency. So 1248.32 times 80%, which is 0.80, is equals to the actual turbine work with the value of 998.66 kilojoules per kilogram. Actual network. So the formula that we are going to use in order to solve for the actual network is WNet is equals to WA minus WP. So WA stands for the actual turbine work and WP stands for the approximate pump work. So we already have the value of these two in our previous solutions. So the WA is equals to 998.66 kilojoules per kilogram and WP is equals to 2.01 kilojoules per kilogram. So WNet is equals to 998.66 kilojoules per kilogram minus 2.01 kilojoules per kilogram. So the value of our actual network will be 996.65 kilojoules per kilogram.
To solve for the actual cycle thermal efficiency, we will be using the formula AC is equals to actual network WNet over heat added QA. The given actual network WNet is equals to 996.66 kilojoule per kilogram, and the given heat added QA is equals to 3496.26 kilojoule per kilogram. And now, substituting it to the formula, we will get EC is equals to 996.66 kilojoule per kilogram over 3,496.26 kilojoule per kilogram. And from that, we will get the value of 0.26.51. Then we will multiply it to 100 to get the equivalent percentage. And now, the actual cycle thermal efficiency is equal to 28.51%. And now, next, for the actual engine thermal efficiency, we will be using the formula ET is equals to actual turbine work, WT, over energy chargeable, EC. The given actual turbine work is equals to 998.66 kilojoule per kilogram, and the given energy chargeable is equals to 3,498.27 kilojoule over kilogram Kelvin. Substituting it to the formula, we will get ET is equals to 998.66 kilojoule per kilogram over 3,498.27 kilojoule per kilogram Kelvin. And from that, we will get a value of 0.28.55. Then we will multiply it to 100 to get the equivalent percentage. And now, the actual engine thermal efficiency is equals to 28.55%. Thank you.
To get the actual entropy, we will first use the formula for the steam quality, with us having a given of H2 is equal to 2,691.44 kJ per kilogram. The formula is X2 is equal to H2 minus specific enthalpy over HFG. Substitute the given to the formula 2,691.44 minus 191.83 over 2,392.8 multiplied by 100 is equal to 104.46%. Take note that the specific enthalpy and HFG can be found in the steam table. And then, solving for the actual entropy, we will be using the formula S2 is equal to specific entropy minus X2 multiplied by SFG is equal to 8.4847 kJ per kilogram Kelvin. Now, we will solve for the actual turbine efficiency. To get the actual turbine efficiency, we will use the formula ES is equal to actual turbine work over ideal turbine work, where actual turbine work is equal to 998.66 divided by ideal turbine work, that is equal to 1248.3 multiplied by 100 is equal to 80%.
To find the actual temperature of the steam at the given exhaust and the actual entropy of the steam at turbine exhaust, we will be doing interpolation. From the previous solution, we have seen that the actual enthalpy on point 2 is 2,691.44 kilojoule per kilogram, which is greater than the specific enthalpy of the saturated vapor, which means that the condition of the steam is superheated. Since the condition is superheated, we need to look on the table 3 on the steam tables, specifically on page 16 at the pressure of 0.010. We need to find where the value of the actual enthalpy is, and it is in between the temperature of 100 and 110. Now, we can make the table needed for the interpolation. From the data on the table, we can now do the interpolation for the actual entropy. The formula will be the actual enthalpy minus the specific enthalpy of the saturated liquid divided by the specific enthalpy of the saturated vapor minus the enthalpy of the saturated liquid equals the actual entropy minus the specific entropy of the saturated liquid divided by the entropy of saturated vapor minus the entropy of saturated liquid. Just substitute the values and you can now put this equation on your scientific calculator, then shift solve. And the final answer will be 8.4584 kilojoule per kilogram Kelvin. There is also another way to solve for the entropy using the steam quality. The equation to get the actual steam quality is actual enthalpy minus the specific enthalpy of the saturated liquid divided by the specific enthalpy of the evaporated liquid. Substitute the values, then multiply to 100 so we can get the percentage. Then, we will going to use the formula actual enthalpy is equals to specific enthalpy of the saturated liquid plus the product of the actual steam quality and the specific enthalpy of the evaporated liquid. Just input the values, then the answer will be 8.48447 kilojoule per kilogram Kelvin. As you can see, there will be a minimal difference on the decimal points of the answers. For getting the actual temperature, we will also use interpolation by using the previous table. The formula will be the actual enthalpy minus the specific enthalpy of the saturated liquid divided by the specific enthalpy of the saturated vapor minus the enthalpy of the saturated liquid equals the actual temperature at point 2 minus the temperature of the saturated liquid divided by the temperature of the saturated vapor minus the temperature of the saturated liquid. Substitute the formula on your calculator using shift solve and the answer will be 102.1 degrees Celsius. For the summarization, this table consists of all the answers with the formula used to get on both ideal and actual Rankine cycle. This will be the end of our group discussion about the ideal Rankine cycle and the actual Rankine cycle, and we hope that whoever will watch this can take something that can help you understand this topic more. Thank you for giving your time to listen and have a good day.